The goal of this part is to put the communication aspect of the smart grid. And we have Christopher joining us. Hello, Christopher. The communication part of the smart grid is largely based on standard communication courses. So that is why we have split this course into two groups, because most of your colleagues did not have a course on computer networking. So in parallel to you now, they're taking a crash course on computer networking. But since you had such a course, we will look at more advanced topics that are specific to the smart grid. Some technical information. There is one textbook that is available on Moodle. It's the textbook called Communication Networks for Smart Grids. It is a very descriptive and quasi-exhaustive set of all the communication parts that exist for the smart grid. It's not very exciting because most of it is describing the technology and the names of the technology that are used in different settings. Most of them are simply doing the things that we know already from a basic computer networking course, but that's very useful if you have a project, for example, to work with, for example, smart meters, and you need to know what exactly are the protocols that are used to pass information from a smart meter to a smart meter concentrator. This book will give you all the standards and the practice here. I give also a reference to network calculus. This is a much more advanced course that is used in the context of time-sensitive networking, which is one aspect of networking for the smart grid that we will cover in detail later today. So both of these are available. The first one is available on Moodle. It's a paying book, so we have it only for you as EPFL students in the context of this course. The other one is in the public domain. So, smart grid is about the grid and about automating the operation of the grid. So first I will start with giving a few typical settings, and I would like to ask you to observe them and think about what is special in terms of communication network for this setting compared to what perhaps you have learned already or practiced in other contexts. Here is a very typical example that is deployed today in most existing advanced infrastructures. It's called Substation Automation. So I would say in pretty much all advanced, in countries that have an advanced or partly automated infrastructure, this is what we can see today. A substation is something like you see here. This is a place where you have high voltage lines that join and are cross-connected. And at the same time, you have a number of equipment to control this. So you have transformers, those are the big visible parts here. And you have the crossbars with switches and circuit breakers. So the switches are the thing that are used for reconnecting the grid when there is, for example, an outage somewhere, or there is a flow, a big change in the flows, in the power flows that require you to change the connection of the grid. So those are the switches. The circuit breakers are the safety mechanisms that are used to open a line when there is a condition, for example, congestion or a fault somewhere on the line. And all of this equipment is controlled electronically. In fact, one of those stations, in Switzerland at least, is not manned. Nobody's there, except when there is some surveillance, monitoring, or some maintenance to do. So it's completely automated. So all those electronic equipments, here are VT and CT, are voltage transformers and current transformers. Those are the devices that are used to measure. You have seen the PNU course in the past weeks. So the PNU is fed by a voltage transformer. We don't measure directly the voltage on the line, but we measure a much lower voltage that is mapped from the line voltage here. So all this monitoring, control, actuation of the circuit breaker and the switches, all this equipment is controlled electronically. So you have computers, embedded computers that control all this equipment and pass the information to a monitoring center, which is in the operation room. There is probably one in this room here, and there's another one that is in the central location of the operator that runs this grid. For example, in Romanel, close to where I am currently now, there is such a big substation that is controlled by Swiss Grid for half of it and by City of Lausanne for, I believe, for the other part of it. So in other offices, you have computers. SCADA stands for Supervisory Control and Acquisition, not sure about the acronym. That's the computer that is used to monitor, to observe what is happening in all of these equipment. So what are possible scenarios that can occur? Well, assume, for example, for some reason, we need to open a line. This will happen when there's a fault condition. For example, a tree is fell on the line, or and then the circuit breaker senses that there's a short circuit through several mechanisms and immediately opens the line. So this information is sent via the local network of the substation, and via a remote area network is sent to the SCADA that now knows that this line is open. Then the SCADA may decide, based on either operator action or sometimes automated algorithm, may decide to open or close a switch. If this line is open, perhaps you want to transfer the power flow that used to flow on this line to another switch to recover from the failure. That may be done, is typically done via emergency plans, though that will happen automatically, but it may also be the result of a human decision. So this is a flow that will go from the SCADA to the actuator here. And probably in parallel to that, in order to assist the decisions that are manual or automated, there will be measurements of the phasors of the grid that will be sent to the SCADA to do what we call state estimation, that you will see in the coming weeks. So this is typical information flows in substation automation. Again, if you have any questions, don't hesitate to ask. Since we're a small committee, you can simply turn your microphone on and speak out. Here's another example, which is spanning several locations. It's called Teleprotection. That's one of the advanced mechanisms that was deployed in the past decades. It's called Teleprotection, where here it is something that is used to monitor the state of a line and take decisions to avoid cascading failures by immediately opening a line that has a problem. And this is done by measuring the voltage, for example, at the complex voltage at the two ends of the line. By doing that, for example, you can detect that if the phase difference is too large, that means there is a problem on this line that is perhaps will cause tripping of other equipment, but before that happens, you may want to simply open this line. So such a fault condition can be obtained by simply comparing the state at two ends of a line here. So of course you need communication. So you have specialized equipment today that will measure every 20 milliseconds here the state of this voltage phasor. We'll compare it by sending it to the other end or to a central location, comparing with the voltage phasor at another end. And if there is a symptom of a fault condition, has to take a decision. Here we have constraints like all of this must happen very quickly within milliseconds. One of the numbers in the standard is 4 milliseconds for such a teleprotection. So that's another example. So the first two examples are examples of automation that have been done since 10 years, perhaps. And what is very new now is coming is something at a higher level, which is motivated by the integration of renewables. Renewables pose problems to a grid. They are, of course, of great societal advantage through fighting against climate change. But the main feature of renewables, at least the new renewables, not hydro, but wind and solar energy, is that they are intermittent. They are not constantly producing. You need to forecast them. And for example, now there is probably not much of solar energy being produced in the area where we live here. So this has to be managed. And the forecasts are always never precise. So the uncertainty of forecasts for renewable is fairly large, is 10 to 20%, depending on the type of renewables, which means that we must react to changes in the forecasts by taking decisions. And one way to do it is to act on all the different elements in the grid. For example, if you have a grid where you have a lot of electric cars that are being charged, so this is a bit futuristic, this is not just emerging in these years, but in 5 to 10 years from now, this will be something that will be very frequent. The electric cars are huge loads. The consumption of electric cars is very large compared to the consumptions of what we're doing now with using power to power our computers and our lights. This is minuscule compared to this. So those are huge loads. If, for example, there is a deficit in solar energy production that is unexpected, that is in this error bounds, then one way to handle it is to send information to all electric cars that are charging to ask them whether they can charge a bit less than they were planning to do. So the management of loads that have some flexibility is something that can be done to adapt consumption to production when the production is random and not entirely cannot be forecast with absolute accuracy here. So automation of electric car charging is one of the big topics that is coming in the short term. So this is what many companies and startups and large companies are working on. Now also there is smart meters and automation of distribution grids. They go together. Smart meters, automation of distribution grids is motivated by the fact that you can have now within the distribution grid, you and I can start having solar panels on the roofs of the place where we live. So we become producers. And that means that the grid, the distribution grid that used to be a completely passive part of the grid now becomes an active one. Again, let's assume there is, I mentioned a few minutes ago, an example where we would have a deficit of production. We were forecasting some amount of production in the grid, and due to forecasting error in solar or wind energy, we don't have quite what we were expecting. That can happen in both directions. We can have too little or too much here. So one idea here is to adapt the consumption, not just of electric cars, but to adapt the behavior of the entire grid. For example, one serious proposal that people are making to address the energy change in Switzerland is to over-dimension dramatically the amount of solar production, based on the idea that the physical cost of the solar panels is minuscule. So we should over-equip the whole of Western European countries with solar panels. Why do we over-provision? Well, because in winter, this is when we need more energy, at least in the cold countries like here, we want to have a lot of solar panels. Right now, probably they would not be producing much, although they would still be producing a bit. But yesterday, for example, there were periods of sunshines where they would be producing. So you want to generate a lot of, as much as you can, of electrical energy in the winter. And you can use solar energy, which is essentially for free. Except that will cause, at other periods of the year, that will cause overproduction problems. So something that perhaps is difficult to accept economically or at a political level, but that's one idea that people have in Switzerland for solving the energy change. Accept the idea that we would overproduce in summer. So what can we do with this overproduction? Of course, we want to be smart and, for example, use it to produce synthetic fuels, hydrogen or synthetic methane. That's one possibility. But certainly what that would cause is overproduction at some periods of the year. Overproduction is as bad as underproduction. It can cause lines and systems to trip and blackouts. So to avoid this, the idea is to manage the production of the grids, of the elements of the grid. That means your solar panel, my solar panel, could receive signals to indicate that it should reduce its production, for example, when there is no need for it, or when that would be putting in danger the stability of the grid. So this is one idea of automating the distribution grid by sending online controls to devices on the grid that can be consumers like electric cars, that can be producers like solar panels. And an indirect way is also to act on the price of energy by allowing what is called smart meters. The idea of this which is very disputed, but an idea is that the price of electricity could vary. If you accept that, it could vary, for example, every 15 minutes based on the state of the grid. That we will see when we talk towards the end of the course, that sending charging price signals is a way to control the power that is sent. For example, that would be a way to control your solar panels. If you receive the information that the energy that you're injecting into the grid has a negative price, that means you have to pay if you send solar panels now because the grid is congested with too much energy being produced. Well, hopefully, if you receive a negative price, you prefer to shut down your solar panels rather than having to pay to inject here. So hopefully your devices are controlled in this way. Another use of that we'll discuss is to what we call shave the peak. If there is a period in time where the consumption is too large compared to the production or becomes very expensive to produce, this is known in the winter, for example, when there are very cold periods in the winter in Western Europe, the energy production is hitting its limit, so it becomes extremely expensive to match demand, and there are systems to send price signals to those customers who agree to consume less during the 2-3 days of the year where this happens here. So that is one way to control the grid here. You may have heard that a few weeks ago in Texas, there was such a case where the entire grid collapsed because essentially the combined gas turbines did not bear the cold. It was too cold compared to how the equipment was installed. The Texan grid is very special in the sense that it has quasi no backup facility and no contingency plan. So that means whenever something goes down, everything collapses, which is what has happened. And those people who had variable, this is implemented in Texas, so you can have, if you want, variable grid tariff. And the grid tariffs were multiplied by a factor of 100 during this event, which means that you were paying $5 per kilowatt hour. You can imagine the kind of bills that you received. So this is why those things are, of course, to be taken with great care, but they are part of the landscape, and certainly with perhaps less adventurous methods than in Texas. They're part of the mechanisms to control the grid and solve the problems of the integration of renewable by orchestrating the entire demand and consumption such that they match each other. The alternative, if we don't have this, is to match by having reserves. So if you have, in winter, you have peaks that require to have much larger consumption, then you need to have, for example, fossil fuel stations that are able to send more energy more power into the grid at the few moments where this happens. Another example that is triggered by the integration of renewables is the end of the afternoon in Europe in summer. So in June, for example, on a sunny day, a large fraction of the energy, this is already happening in countries like Italy that has a large deployment of solar panels, a large fraction of the energy produced in June in the afternoon comes from solar panels. But the solar panels, they stop in the evening, so at 9 o'clock in the evening, the production goes quasi to zero. But this is when people are starting to use at least as much energy as before. So restaurants are working, lights are turned on, perhaps air conditioning is also turned on. So there's a huge increase in the consumption. That's called a ramp of the consumption that occurs within 1 or 2 hours. So you need to start huge amounts of resource during a short period of time. That costs a lot of money. So an alternative is also to modulate the consumption, for example, by, if you have electric cars, to leverage on them to avoid this peak and thus reduce the costs of the reintegration of renewables. So the smart grid, because of that, is at the heart of the integration of renewable. If we want a grid that lives on a large fraction of renewables, we will need to do such things. So back to communication, here is another folklore aspect of smart grid communication. If you go to a smart grid substation, like the one I mentioned in Romanel, you will see things like this. You will see, for example, an embedded computer that might control some of the equipment, and embedded controllers that, for example, close or open a switch, that are, as I said, they communicate with each other. Many of them still today don't communicate exactly the way we saw in the course on TCP-IP. In the classical way of communication with TCP-IP is you communicate by definition at the application layer, because that's the goal of the application layer. And the application layer uses the transport layer, because that's the function of the transport layer. The transport layer is providing a service to the application to use the network. But in I would say old equipment, but a lot of them are still existing, the application layer is written directly on the MAC layer, on layer 2. So you will have, for example, on the substation, you typically would have an Ethernet, no IP addresses. So everything runs directly on Ethernet, including the application that don't use sockets like you did probably if you had a computer networking course. If you had it at EPFL, you had the course where you program in Python to sockets. Here you don't do this. You use the alternative environment to sockets that directly send MAC frames instead of IP packets. Of course, if you do that, it's very similar to using UDP in the sense that the MAC layer allows you to send a packet to another destination. After all, it works. It's true, you don't need IP for that. You will not have TCP. That means that this system will need to embed the reliability. Most of the times, devices like this use what is called multicast. So the packet will be sent not just to, for example, not just to one switch controller, but perhaps to several switch controllers. So this is done, I would say, in the legacy environments, because many of the electricity sector actors make the equation that layer 2 is hardware and layer 3 is software. So whenever they do hardware for automation, they will never use IP. If they use IP, they will do it in software. This is an extreme view of things. It does not correspond to reality. You have vendors that make, for example, TCP-IP chips that can implement everything in hardware. But this is how some of the, I would say most of the industry in the electricity sector thinks. So if you work in a substation environment, you will be confronted with that. But other than that, everything you have learned about computer networking continues to work, because after all, a MAC layer is a way to build a network. What is the benefit compared to IP? Well, for example, the addressing scheme here is much simpler. You know that with MAC addresses, once you know the MAC address here, you can avoid protocols like ARP, DNS, etc. Of course, it's also a bit clumsy. You need to write in MAC addresses. You don't speak to controller X. You speak to controller that has this given MAC address. So I have done a little show on what is a smart grid here. So now it's your turn to think about what do you think compared to computer networking is special to computer networking at large, like we use when we use Zoom or we go on the web, is specific to smart grid applications. Here I'm inviting you to use a feature of Zoom, which is called Annotate. So if you go to the Zoom menu somewhere, you should find an Annotate menu. And if you click on the Annotate submenu text, then you can input your own text into this slide. Voila, it's your turn. Distributed computation at client's location. Good. Don't be shy, it's anonymous, at least for me, so I don't see who writes what. Coordination to avoid cascades. Good. Or tragedy of the commons. It's not clear to me what you mean by that.
I mean, I can explain what I mean.
Yes, please.
It was my way to, in few words, say how greedy algorithms can cause suboptimal solutions at like a global scale. So if you have like smart charging algorithms and they all try to do the same thing at the same time, you can have really bad effects on the network as a whole. Even though it is the optimal solution for each one, it does cause a overall bad solution, and that's how like the tragedy of the commons.
Excellent, excellent. So the cost of anarchy, if every actor optimizes its own selfish interest, the overall behavior for the grid will be what is called tragedy of the commons. It's the common good will be in danger. Exactly. And that's one of the causes of cascading failures in the smart grid. Exactly. If you this is why you need some distributed mechanisms, which you have mentioned here. Excellent. Resilient state management. Operator and client agree on what has happened. Excellent, yes. But there is another aspect that I will mention now. If I find the, so I need to stop the annotation. How do I? Here, more. Okay, so I stopped the annotation. If I find my annotation menu. Here it is. Oops. So I need to clear the annotation. Voila. Everything you said is perfectly right and is essentially at the application layer, on the semantic level of the smart grid. So it has to do with things you will see in the coming weeks with Mario on state estimation. Then you will see with me on optimal power flow, how we decide what to do in the grid based on what we see. But if we go to the bits and pieces of the communication system itself, we will see a number of features. One is security. So we'll talk about it next week. Security is, from the communication viewpoint, the most important aspect of the smart grid, or of any critical infrastructure, or in fact of any communication system today. So the lab that you will do, the second part of the lab that you will do for the advanced group will be about mounting an attack against a smart grid and how to prevent this attack. But right now, what we will discuss is things that are related to delay and loss. So if you think about the teleprotection application, for example, that requires a relay to send a packet to another, requires a sensor to measure a voltage and compare it to the voltage received from another sensor. What happens if this packet is lost? Of course, the application will detect the loss and will send it again. But you have to make sure that this happens with very low delay, because if sending the packet takes some time, and if you use TCP with head of the line blocking, if it takes 20 or 30 milliseconds, then you miss the deadline. So the very low delay for some application is one aspect. And also the negligible loss, so what is called absence of congestion loss. Of course, you can always lose packets if you lose the line. For example, if you break the communication line, then you've lost communication. But if that happens, we will detect that the line is broken and we will declare that we will start operating in degraded mode. What you don't want is that you lose a packet simply because of a buffer overflow in a router or a switch buffer here. So the standard internet traffic control, where if you remember, loss is one, together with ECN, is one of the signals that is used to control the rate at which sources are sending. So this will not work in the context of smart grids. So we will need to discuss how traffic control is done. It's done in a different way. Then there's also reliability that we will discuss a bit. What happens if you break a line, then of course this line is completely unusable. If this communication line is very important, you may need to duplicate the line, for example. How this is done, we will discuss a bit later. Then there's the integration of non-IP services, how they move to IP. That's one of the topics that is keeping people busy in the smart grid today. Much of the tradition in this industry has been to do applications on hardware, so without IP, and now that those things are developed, you need to migrate them here. We'll talk about MPLS. That's a new topic, which is a bit peripheral in a computer networking course, but in the context of a smart grid is an important protocol. And also you need to distribute time. Why do you need to distribute time in a smart grid?
I mean, isn't that part of what we did with the PMUs, where you need to agree on what happened when? Exactly.
On the PMU, you measure a time shift. You measure offset of a sine wave, right? So for that, you need to have the same time in all the PMUs. If you have only one PMU, there's no problem. But typically, you want to measure not just voltage and current at one PMU, but at multiple PMUs. So you need to synchronize the time at different PMUs. So PMUs receive time from GPS typically, or from networking from the network itself through network time protocols that we will discuss briefly. You discussed with Mario the timing application. We'll discuss the network application of time distribution. So those are the things that make the smart grid what we call an industrial network. So the smart grid is not, from the networking viewpoint, it's not very different from other industrial networks that are used, for example, at small scale in airplanes. So all the most recent airplanes, the most recent Boeing or Airbus, they use an embedded network that is very similar to that uses how similar requirements as we have here, with the difference that it's a small scale network, so it's similar to what we have in a substation automation. Smart factories, when you have factory, for example, the new factory that builds the vaccines now in Switzerland is completely automated, so it also has a network. And factories tend to act also very quickly. So if a robot somewhere is doing something, and this action is not isolated, so it must do it because it has sensed that some condition were requiring it to do this action now. So you have an orchestration that is real time. So the transfer times are similar to what we have seen in the smart grid, order of a few milliseconds. So the smart grid in general is, from the communication network layer, is an example of what we call an industrial network. And there's huge developments now in industrial networks for automation of planes, cars, trains, factories, etc. The smart grid being the bigger of those industrial networks. So what I propose now is that before we dive into the specifics of the smart grid, is that we do a small refresher on TCP-IP. So we will do 7 or 8 quizzes. We will not do the quiz using quizzing system that we used before, but you can simply use this annotation feature. So I don't see the names of the annotators, so you can simply write your answer on this slide. We are 5 in total, so please go ahead. Question 1 is here. I'm showing smart grid automation. It's a picture that's taken from the book that I recommend on the smart grid, showing two devices, A and B, and they communicate over a network of Ethernet switches here. At observation point 1, we put a packet sniffer. Which MAC destination address will we see? So I have 3 answers. One more, please. Okay, time out. So we have 2 votes for B and 1 vote for C. And the correct answer is B. And why is it B? Well, because that's by definition of bridges. Bridges are transparent. Ethernet switches are bridges. So when A sends a packet, it sends it by putting the destination address, MAC address B, and since the switches are transparent, that's one way to recall things, you don't send the packet to the switch, you send the packet to B. The switch will take care of finding how to send it to B. We've seen that the switch will learn and will build a spanning tree. So this is how the switches will know that the packet has to be sent to B. Okay, so move to next question. Whoops, I need to clear this. Well, now I have a slightly smaller network. So small networks tend to have only Ethernet switches. Larger networks will have routers. I assume here at the point, the blue point there is a router. And with same question, we see the packet at point 2. What do we see in the addresses? Three out of 3 says router's MAC address and A's IP address, which is correct. So this is how IP and the MAC layer interact. The principles of the IP layer is that the IP layer separates Ethernet domains. So A sends to the router from the viewpoint of Ethernet, and the router sends to B from the viewpoint of Ethernet. So at 2, you will see a packet at the MAC layer coming from the router. But of course, at the IP layer, it happens exactly the same way as in the previous slide, but where the IP layer takes the role of the MAC layer, and A sends the IP address is the IP address of A. Excellent. Clear all drawings and continue. Virtual LANs. Here I'm assuming I have a switch here, and there are virtual LANs. So virtual LANs is something that's also very often used in substation automation, because by being only at the MAC layer, we have lost all the flexibility of the IP layer. And part of this flexibility we regain by creating what is called virtual LANs. So a quick reminder, a virtual LAN is something that allows devices connected to the same switch to be isolated, as if they would not be connected to the same switch. Right? So C and D believe they are on one switch, A and Y believe they are on another switch, but it is as if C and D were connected, as if switch S1 was in fact a green and a red switch duplicated here. Now assume A has an IP packet to send to C. Right? What should A do? Seems to be puzzling, right? A and B. Okay, I close in a second. The correct answer is neither A nor B, because, as I said, a virtual LAN separates the LAN. So as I said, the red and the green LAN are truly separated. So if you have only this, if you have only a switch with two virtual LANs, they cannot communicate together. It's as if you had two Ethernet networks and there is nothing in between, then they cannot talk to each other. So then you must have a router, because the principles of IP, one of the principles of IP is between two Ethernets, either you bridge them together and they become one big Ethernet, or you put the router in between. So the correct answer is there must be a router, and when A sends a packet to C, A may first send the packet to the router, which means to the MAC address of the router. In practice, when you have virtual LANs, you have S1 and R in the same box. Although you can, of course, have S1 and R separated, that happens, but most of the time, R is just a piece of software or even hardware inside the same box. So in practice, A sends a packet that goes directly to C, but if you analyze the MAC addresses, you will see that the MAC destination address of the packet sent by A would be to a device inside S1 that acts as a router. Okay. Here's an example where I have smart meters. Smart meters communicate typically over the power lines using communication as a mixture of wireless and wired. So it is wired in the sense that the communication signals goes over the power lines, but it's wireless in the sense that it radiates also in free space. For example, if you have two electrical cables that are together, but that are insulated, they are not in the same, it's not the same phase, for example, then the signal can jump from one cable to the other. So that's power line communication. That is very efficient whenever you find it too complicated to lay cable. So that's used, perhaps the most well-known use by everyone is when you have at home to TV distribution from the operator. You typically receive a power line modem that you can put in a power socket at home, and then you're close to your ADSL modem, and then you can distribute the TV signal, which is IP signal, over power line communication to the room where your TV is. So that's one of the very popular application. But the other one is to communicate with smart meters. So here I'm assuming the smart meters in a given neighborhood are all coming. Of course, power line communication is limited in quality. It works at home on very short distances to 10, 20 megabits per second. On long distances, or I would say medium distances in a neighborhood, if you have cables of 1 kilometer or so, you will have extremely small bit rates. So typically you go only to the next hop, that is a router. And then the router that is somewhere in the boxes that belong to the utility that runs your network will go over optical fiber to the communication center of the utility, where you will have computers, for example, a smart meter management system that will gather all the information. Now, assume that we use, which is very often done, we use multicast. For example, if the smart meters are used to update, to have variable prices, the price is repeated every few seconds by the head end that sends a message to all smart meters at the time. So it will typically use multicast. So if we use multicast, what are the things that A and B that I say is likely to happen? I'll let you discover the text and vote for one or the other. Two answers for B. What do the other two think? Okay, let's close the poll. Thank you. So Dirac on B, which is the correct answer. So with multicast, it is the destination that joins. So that was a quick reminder on how IP multicast works. So multicast is very frequently used in smart grids. I give an example with communication that's broadcast to all the meters in a given neighborhood, or to perhaps not broadcast, only send to a specific neighborhood, not the entire network here. It is also used, for example, in substation automation, when you have a device that sends information, a sensor, a PMU, for example, measures something, then the PMU typically has to send the information to several systems, at least two in general. One is the PMU concentrator, the PDC, that receives all the data from the PMUs, will check them, do bad data detection perhaps, time align them, etc. But also to the SCADA in parallel. So one of the things we find in industrial automation is that you typically have an application that uses the data, but you also have monitoring, where you try to you want to observe everything that happens. And this is typically done by a different system, because you don't trust 100% the application. The application may go wrong. You need to have diagnostic for anything that can go wrong. So in very frequent cases, you have at least two destinations. The SCADA wants to see all the information, but also the control logic of the application for which you have the sensor. Sometimes you also have control logic that may require multiple applications. For example, for reliability, you might have two PDCs, and then you send the information not just to one, but to two. In that case, you must send the information to three. So this is why multicast is very frequently used in industrial applications. If it's okay with you, we've reached the time of the break. We will do a break, but if it's okay with you, we have 2 or 3 more questions, then I will continue them, and then we'll do a break after that. Oh, I'm just seeing on the chat that Mathilde cannot write on the screen. You can also use the chat, Mathilde, if you want to give your answer. That works as well for me. So here's another question. What you often find in the smart grid is concentrators for reasons like the quality of the power line communication is limited in distance, so you don't want to run all the way to the main center of the operation. Also, the companies like to centralize things for various reasons, but typically the data and control center is at the headquarters of the company, at least for medium-sized companies like we have in Switzerland. So you want to centralize in one place all your computers, all your experts, telecom experts, data management experts. So you don't want to have devices everywhere. So you will put a meter concentrator here. That's the name that is very often used. If we apply the TCP-IP principles, what should the meter concentrator be? A switch, a router, an application layer gateway, or something else? So we have one answer on the chat that says B, another answer on the screen that says A, another one that says B. By the way, if you find more convenient to use the chat, you can use the chat. The only difference is it will not be anonymous. So 1 vote for A, 2 votes for B, 3 votes for B, so we're complete. And the correct answer is B. So the principle on which the internet is built is that the routers make the network with the switches below them, and the application are end-to-end. In reality, in the smart grid, what we will often find is a violation of this. So meter concentrators are typically application layer gateways, which is not, in principle, what should be done. There's 2 reasons for that, one good, one bad. The good reason is to decouple the hardware from the software. And in particular, this is something we find in grid networks. In the computer networking world, things are essentially software and they change all the time. You have a new app that comes, or Google decides to invent Quick instead and use it instead of TCP. Okay, all the Google browsers and the YouTube apps switch to Quick, and most people don't even know that this switch has taken place. So the things change very frequently. The same is happening in the smart grid. When you do smart meters, those are computerized equipment that talk to a center. So they have a protocol. They have an application layer protocol, also physical layer for communication, etc. So all that stuff is implemented in the smart meter. But the lifetime of such equipment is much larger, and you don't want to update the software in them very frequently. So what typically happens is that they remain much more rigid. And if you change the software somewhere in the head end, for example, where you change from one application to another one, you don't want to change all your smart meters. So very often you put a meter concentrator for isolating from the software viewpoint the meters that are perhaps were deployed 3 years ago, which is a now obsoleted type of meter. New meters are according to a new type. They use a different version of your system. In that case, it's the meter concentrator that will continue to talk the old protocol to the meters and will talk the new protocol. So that's one of the reasons that's used for that. That's the good reason. Well, the bad reason is that very often people like to sell hardware. So when they sell meters together with a meter concentrator without realizing that very often that is in fact not needed. So if some of you are interested in businesses, perhaps there's a way to save money in the smart grid by streamlining all the hardware, which is still based on the tradition in the electricity sector to sell functions in hardware rather than software. Good. Move on to the next question. A traffic control or a traffic specific TCP specific issue now. The smart grid is used for all the functions I said, but also for the other functions that we use for network. If you're a utility and you set up a communication network, typically it means you set up optical fibers along the lines. So all the utilities have conduits where they place power lines. Of course, they use the same conduits to put also optical fiber for the communication. Once you have optical fiber, you can use it for all the things that we use in the internet, like for doing, for example, video streaming. So you have in the unmanned substations, you have cameras, and in the surveillance center, the monitoring center of the utility, you typically have video walls where you see what is happening in all the substations. So these cameras also will go via the communication network of the smart grid to pass the information. And I'm assuming one IP camera streams to the video wall and uses TCP, which is very commonly used. But one packet containing video frame number N is lost. Then what happened next to the rest of the video frames? I'm assuming, if you want, that one video frame fits in one packet. So frames N, N+1, N+2, etc. are not lost. What will happen? C, 2A, and the correct answer is A. So here what will happen is that, so let me, because of the in-sequence service of TCP, if a packet is lost, TCP will stupidly, perhaps, but that's the nature of the streaming service, will not deliver the data that were sent after. So if packet N is lost, on the receiving end, the video will freeze until the loss is repaired if we use TCP, which is very often the case here. So it will cause large delays. Depending on the size of the network, it may be up to a few seconds. And that's one of the issues in the smart grid, that's the use of TCP. As when we move to IP, we have the choice of using UDP or TCP. If we use TCP, we have this head-of-the-line blocking, which is why many applications that have real-time requirements use UDP. So PMUs, when they stream to the PDC, will typically use UDP. And of course, you will need a mechanism to detect losses. So you will typically put an application layer acknowledgement and retransmit at the application layer, where you can benefit here from doing it at the application layer. For example, if you're a PMU, you send one packet every 20 milliseconds. If a packet is lost, you try to retransmit it. But if a new measurement comes and you have still not received an acknowledgement from the previous measurement, what should you do? Should you insist on trying to retransmit the new measurement? Probably not. What you want to do is simply send the newer one. The old one that is lost is obsoleted by the fact that you received a new one. So if you do it at the application layer, you can optimize, but of course it's more complicated. So this is what you probably will need to do in this context. Now back to a larger scale network, my meter concentrator network. Assume the capacity of the neighborhood area network is not large, which is typically the case because it's using power line communication, which is very low capacity when you extend it to medium size, to an entire neighborhood, as opposed to inside your apartment from one socket to the other. So the capacity has been engineered and is just okay, perhaps with a small safety margin, when all meters are working normally. So meters normally send data at a rate R. But now there's a bug. There's this red meter here that has a bug. It becomes what is called a babbling idiot. This is one of the horror cases in substation automation, in industrial networks in general. If for whatever reason, a device sends much more traffic. That seems stupid, and why would a device do that? But computerized device, sometimes they look stupid to human beings. And that can happen. For example, there is a programming error or an error in the hardware. There's a loop that's sending a message. And this loop, instead of saying, wait until you've received something, a signal here, then it blocks and keeps sending and sending and sending again. So this is so well known in the smart grid context, it's called a babbling idiot. It's a device that becomes an idiot and sends traffic all the time. So this meter is a babbling idiot. It sends UDP data at a rate which is as large as it can, which is probably when you use power line communication, you typically have an Ethernet connection from the device to the power line modem. So it will send at the speed of Ethernet at 100 megabit per second, which is a much larger rate. So assuming the babbling idiot part of the meter is UDP. So it has perhaps a small UDP application that's used for something that normally does not send much, but here it sends a lot. What will happen? I'm proposing 3 possible catastrophe scenarios. Large concentration on B, which is probably here the correct answer. I say probably because in reality, there may be a lot of hidden assumptions, but probably what happens here is if the network, if the network is a plain network without traffic engineering, like we will see in a few more minutes, it will treat all flows the same, so this will flood the buffers of the switches and routers and will create a lot of losses. Now, because the other meters are using TCP, TCP runs congestion control and will adapt. So TCP will see, oh, there is less capacity available, so all meters will send much, much less. We can compute exactly how much there will be. The available capacity is C minus R max. If this red meter is able to send at the rate R max, and if this is less than C, well, the available capacity will be divided between the other meters. And since the original capacity was close to NR, this will be much, much less than R. So that's one of the problems that you need to address in an industrial network in general. What happens if, for whatever reason, one of the devices is using all the capacity for itself and the other devices are adapting? Then they will be sending at a smaller rate, which perhaps will make them unusable. If the smart meter is using TCP to display information, for example, perhaps the connection will be broken and the logic of the application will not work well. Voila, last question of this long quiz. Imagine you're hired by a company, Romand d'Énergie or Service Industriel de Lausanne or de Genève, and instead they want to upgrade the equipment that they have that works only on the MAC layer to IP. Why do they want to do this? Perhaps because they want to change from using providers that sell hardware that's very expensive to software that is less, to software computer-based solutions that are less expensive, or perhaps because the network has become so large that at one point it becomes very clumsy to use only Ethernet. So you want to move your protocol, like GOOS is this application layer protocol specific of Substation that specifies how a controller speaks to an actuator, which runs, if you remember, only on Mac. You want to move it to IP. So which combination would you use? Two Bs so far, 3 Bs, 4 Bs, which is perfectly correct. That would be probably the only thing to do. This is using multicast, so we must use multicast. If we use multicast, we must use UDP. So UDP and IP multicast is a good combination. Even if it would be unicast, probably we would use UDP and IP unicast, except if you want to change radically the software. So probably your GOOS software was working on Mac, and Mac is very similar to UDP. With the Mac layer, you have to specify a destination MAC address, and then you send the frame, which is what we do with UDP. With UDP, we have to specify an IP address and a port number. So you will need to change the addressing system. But other than that, the logic of the application can be kept exactly the same.